Hello friends, welcome back. We are looking at various types of branch and bound problems. In this today we will see how traveling salesperson problem can be solved using branch and bound. As an example, let us take a 5 city problem where we have cities 1 to 5 and this is the distance matrix we have, and the major aim of branch and bound version of solving this problem is one, looking from the source side, from any source, say node 1. If you ask somebody from node 1 where do you want to go, so definitely the answer would be want to go to node 4 because that's the smallest distance. Same way, if you ask from node 3, if you ask anybody where do you want to go, so definitely the answer would be would like to go to node 2, node 4 because the distance is minimum. So that way, these are the minimum distances. So if you find out what are the minimum distances, then we get 10 in the first row, 2 in the second row, 2 in the third row, 3 in the fourth row, and 4 in the fifth row. And then let us subtract these values from each row. So then we get this matrix. So 20 minus 10 is 10, 30 minus 10 is 20, 10 minus 10 is 0, 11 minus 10 is 1, and so on. So once this is done, then we would like to ask the question, so if you want to go to say node 1, then from where you would like to go? So obviously the answer is we would like to go from node 3 to node 1. Same way, if you ask if you want to go to node 2, which is your preferred node, from where you want to go to node 2, then the obvious answer would be node 5 because the distance is 0. So that way, if you look at it, then we can find out the minimum distances for each column. So we get a 1, 0, 3, 0, 0. So in all, what are we trying to look at is, if you start from 1, we can go to 2, we can go to 3, we can go to 4, and we can go to 5. And at the end, we need to reach 1 back. So this we can do it from 2, do it from 3, do it from 4, or do it from 5. Now thing is, if you start from 1, where do you want to go? And if you end at 1, from where you want to come? So that's one we are looking at, and that's what we just tried to find out. So from 1, each node, where do you want to go next? That's row wise minimum. And from each column, it says that if you want to go to that node, from where you want to go, that is if you want to reach 1, from where 2, 3, 4, or 5. So we get one information about where do you want to go, and another information from where you want to return there. So these two are considered together simultaneously, and hence this overall work is done. So the final matrix we get is, after subtracting 1 from the first column and 3 from the third column, because other 3 values are zeros, so we get this particular matrix. So we have 20 minus 3 is 17, 14 minus 3 is 11, 15 minus 3 is 12, 3 minus 3 is 0. So that's what we have here. So looking this. So how much we have totally reduced? So 10 to 12 to 14, then 17, 21 row wise and 4 column wise. So that makes total cost reduction is 25. So from first node, if you look at it, so at the beginning we have a cost of 25. So let's begin our journey. So for this, the cost is 25. Then from here, we can go to 2. So that's our node 1. We can go to 3. We can go to 4. We can go to 5. So these are node numbers 3, 4, and 5 for this tree. The next nodes in the next level will be 6 onwards. So wherever they come, we'll take it. So the first thing we want to know is what is the cost of traveling from 1 to 2. So for that, we take up this exercise. So this table is used, and in this table, what we say is you are starting from 1 and we are going to 2. 1 to 2, starting from 1, going to 2. So 1 to 2 is our concern. Therefore, 1 to any other thing should not disturb us while finding minimum. Therefore, forcibly we make first column all values infinite. Then from 1 only we should come to 2. That means no other node should lead us to 2. So to make sure that from no other node you come to 2, let's make all values in the column 2 as infinite. That means from any node we cannot come to this because we are looking for minimum. So when you say infinite, so definitely this will never be selected. Then second thing is 2 to 1 we don't want because it's going to complete a cycle. So 2 to 1 also is made infinite. All other values are just copied from this matrix. And then repeat same thing. So this is our infinite row, nothing to worry about it. On this row we have a 0 minimum, we have a 0 minimum, we have a 0 minimum, we have a 0 minimum. Therefore, we don't have to modify anything as we did here, subtracting that. So nothing is to be subtracted. Then look from column wise. So we get a 0 on this column. This is not to worry. A 0 here, a 0 here, 0 here. That makes the total extra cost reduced in this is 0. So now if I want to find out the cost from 1 to 2 is cost from 1 to 2 plus cost of 1 plus any cost you have reduced at this level. Okay, from 1 to 2, if you look at it, 1 to 2, it is 10. Cost of 1 is, we just found out in the beginning, that is 25, and that makes 35. So this 25, cost of this is 35. Same way, now going from 1 to 3, look from 1 to 3. So first row, third column are made infinite. 3 to 1 is made infinite. Other things are copied from this matrix. So other things are copied from this matrix. So then find minimums. So each row is having 0, so nothing to vary in this matrix. But column wise, when you see, then the minimum was 11 in this row, in this column, 0, not to worry, 0, 0. So this 11 is minimum, so make it normalized. So remove this 11 from the first column. So subtract 11 from this. So this becomes 0, this becomes 4, this becomes 1, and this 11 plus 0 plus 0 plus 0 plus 0. So that's 11 will be our C star for the node 3. So if you want to compute this C13, then it is C 1, 2, 3 plus C of 1 plus C dash of 3. 1, 2, 3, looking from here, first row, third column, that is 17 plus 25 plus 11, that makes 53. So that's cost is 53. Okay. Back to next one, 1 to 4. 1 to 4, same thing repeated. First row infinite, fourth column infinite, then find the minimums row wise, all are 0. Find minimums column wise, all are 0. So C dash is 0. Therefore, C 1, 4 will be C 1 to 4 plus C of 1 plus C dash of 4. So if you look at 1 to 4 in this matrix, 1 to 4 is 0, then this is 25, and then this was 0, so that makes 25. So 1 to 4 is 25. Then finally 1 to 5, if you look at it, so first row, fifth column is made infinite, then minimum here is 2, minimum here is 0, minimum here 3, minimum here 0. So subtract 2 from this row, so 12 becomes 10, 11 becomes 9, 2 becomes 0, then subtract 3 from this, 15 becomes 12, 3 becomes 0, 12 becomes 9. So finally we have C dash as 2. Okay, then C of 1, 5 is C of 1 to 5 plus C of 1 plus C dash of 5. C of 1 to 5 from this matrix, 1 to 5 is 1 plus 25 plus 2. No, sorry, this is 5. So that is 5, and that makes total equal to 31. So for 1 to 5, the cost is 31. Now if we continue this work in the first in first out order, then the next one to find expand is node 2. If you work on last in first out words, then node 5 has to be expanded, and both of them are not an efficient way of working. So the best way of working is least cost. So let us use least cost method. So the cost of reaching 2 is 35, cost of reaching 3 is 53, and cost of reaching 4 is 25, cost of reaching 5 is 31. So among them 25 happens to be the smallest. Therefore we can extend. So 1 is over, 4 is over. Now we are left with going to 2 or going to 3 or going to 5. So fifth node we have. So this will be sixth node, seventh node, eighth node. So now next thing is to look at 1 to 4, 4 to 2. What would be the situation? 1 to 4, 4 to 2. Yeah, it is here. 1 to 4, 4 to 2. So first row, it starts from first row. So first row is start from node 1. So first row is infinite and goes to fourth node. So column 4 is infinite. Then in the next hop, it starts from node 4. So row 4 is infinite. It reaches node 2. So column 2 is infinite. Then we don't want a return path from 2 to 1. So 2 to 1 is also made infinite. Then continued Other things we are copying from 1 4 now. So from this we are copying. So 0 here, 0 here, 0 here, 0 0 0. So the cost of this is 0. So cost of 1 4 2 will be cost of 1 4 2 2, and then cost of 4 2 2 plus cost of 1 4 plus the cost of reaching this 2 additional cost we talk about. Now 1 to 4. In that, what do we want? 4 to 2. We want 4 to 2 in 1 to 4. So that is 3. So this is 3 and 1 4 was 25. And here it is 0. So that makes 28. So reaching this one is first is 28. Okay. Next 1 4 3, that is going to node 7. If you look at 1 4 3, so first row, fourth column made infinite, fourth row, third column made infinite, then 3 to 1 not allowed. So remaining things we have copied. So first row, the second row 0, third row 2, fourth row not in all infinite, fifth row is 0. Therefore this has to be corrected. So 3 reduced to 1, 2 reduced to 0, and then column wise if you look at it, then we get a 11 in the, this is 12, this is 11, so we get 11 in the first column, 0 dash dash, then 0 in the last column. So you remove this 11, so 12 becomes 1 and 11 becomes 0. So total is this 2 plus this 11, that is 13. Now cost of 1 4 3 will be cost of 4 to 3 plus cost of 1 4 plus cost of reaching 3 in this case. So 4 to 3 from your 1 to 4 case, 4 to 3 is 12. Cost of 1 4 was 25 plus 13, so that makes 50. So cost of this is 50. Then finally 1 4 5. If you look at 1 4 5, then first row, fourth column, fourth row, fifth column are made infinite, and 5 to 1 is made infinite. So we have 11 minimum in this row, then 0 dash 0. So 11 should be made 0. So subtracted 11 from this row. So this becomes 1, this becomes 0. Now column wise 0, 0, 0, dash dash. So total is 11. So the cost of 1 4 5 will be cost of 4 to 5 plus cost of 1 4 plus cost of 5. So 4 to 5, if you look at here in 1 to 4, so 4 to 5 is 0, 1 to 4 is 25, and cost of 5 is 11, so that makes 36. So cost of this 36. Now what all we are left with? So the node 2 we have, whose cost is 35. Node 3 we are left with, whose cost is 53. Then node 6 we have, whose cost is 28. Node 7 cost is 50. Node 8 cost is 36. And node 5 is still unaddressed. So 31. Among this, we find that node 6 is the least one. Therefore, we can continue working with node 6, expand node 6. So from node 6, where all you can go? 1, 4, 2 is over. So we are left with 3 or 5. So 8. So this is 9th node, 10th node in this. So we look at 1, 4, 2, 3. 1, 4, 2, 3. So first row, fourth column, fourth row, second column, second row, third column, all are made infinite. Then 3 to 1 is also made infinite. Then other things are copied. So we are left with a few values. This row has got minimum of 2. This row has got minimum of 11. So subtracting this becomes 0. This becomes 0. Column wise, both of them will be 0. So we are left with 13 here. So C of 1, 4, 2, 3 will be C of 2 to 3 plus C of 1, 4, 2 plus C dash of 3. So 1, 4, 2 matrix. Yeah, 1, 4, 2 matrix. In that what we want? 2, 2, 3. So this is 1, 4, 2 matrix. From 2 to 3 it is 11 plus 1, 4, 2. What was 1, 4, 2? 28 plus 13. So that makes 32, 31, 32. So 28 plus 3, 31, 41, 42, 52. Sorry. So that makes a cost of 52. Then looking for 1425. 1425, we find that this minimum 0, this minimum 0, minimum 0. So C dash is 0. Therefore, C 1425 is C 225 plus C 142 plus C dash of 5. So 225 in 142. 142, 225 is 0. 142 is 28. C dash is 0. So therefore this is 28. Okay, now what are left? 35, 53, 52, 28, 50, 36, 31. Therefore, this is found to be minimum. So what all we have? 1, 4, 2, 5. So we are now left with only one node, that is 3. We can call it the 11th node. So if you just look for 1, 4, 2, 5, 3, 1, 4, 2, 5, 3, then you see that all elements are infinite. So this is going to be 0. So C of 1, 4, 2, 5, 3 is equal to C of 5 to 3 plus C of 1, 4, 2, 5 plus C of 3. Okay. So from 1, 4 to 5, what is 5 to 3? 1, 4 to 5, 5 to 3 is 0. And this is 28. And this is 0. Therefore, this becomes 28. Now, we have reached one leaf node. So that's one possible solution. We are not sure whether this can be the best solution or not. So to make sure that this is best solution, you just look at what others are. So we have reached a solution of 28. So now look at this. So this is having a value more than 28. So prune this. This has got more than 28. Prune this. This has got more than 28. Prune this. This is more than 28. Prune this. More than 28. Prune this. More than 28. Prune this. Therefore, no node is left for expansion. So that's the end of it. So it says the solution is 1 to 4, 4 to 2, 2 to 5, 5 to 3, and from 3 back to 1. Okay, what is 1 to 4? So back to our original problem. So it said solution is, okay, take this out so that it becomes easier for us to look at our final solution, compare with the correct one. So the thing says 1 to 4, 4 to 2, 2 to 5, 5 to 3, and 3 back to 1. So 1 to 4, what is it? 1 to 4 is 10. So look from the original one. 1 to 4 is 10. 4 to 2 is 6. 2 to 5 is 2. 5 to 3 is 7. And finally 3 to 1 is 3. So 10 plus 6, 16 plus 2, 18. 18 plus 10, 28. So 28 is the correct answer, and the same 28 we got here. Now if you look at it, go back, it says 28, go back, it says 28. So this is the first time where you talked about 28. That means before, in 2 steps in advance, you could identify that the correct answer could be 28. How was that possible? Because that was possible because of branch and bond. And here the logic was, you are trying to identify from any node what is your favorite node you want to go, and to any node which is your favorite node from where you want to go. So you are looking in the 1, 2 onwards also, and at the end from where you want to end the journey, that also you are looking simultaneously, and because of which we could get it in advance. That is at 2 steps before only we could say that 28 is coming, 28 we are just getting 28, 28, 28. So that's the power of branch and bound. So it is working on 2 steps. One talk about the forward journey and one talk about the backward journey. So it looks at till now what has happened, and then it forecasts what could happen in future. So that's the method of solving a traveling salesperson problem using branch and bound. So thank you for your visiting this particular session. Thank you.